Hello to everyone. We are Alessandro and Giulia, and today we will talk to you about our work at CERN here on the gas electron multipliers or GEMs.
But before we can talk about GEMs, we have to understand how a gaseous detector works. So this is how. We have obviously a gaseous chamber, which is filled with gas. And there is a very sharp electric field that runs into it. And then there are these radiations that eat the particles of the gas and ionize these particles, creating electron a positive ion pair. At this point, the electrons multiply and accelerate thanks to the electric field, and then drift towards the anode, where they, how can I say, they leave a signal that then is analyzed. Let's talk now about the main argument, that is GEMS. The gas used in GEMS is made of 70% of argon and 30% of CO2. The structure is made with foils. There is an insulating layer with conductors on the top and on the bottom. And in the GEMS, there are different layers. Every layer is with a different voltage, so that the electrons can move throughout the gem. In these layers, there are some microscopic holes where the electron pass, accelerating and multiplying. We can see it with this simple graphic. The electrons start from the top, from the drift cathode, then they move towards the Gem 1, Gem 2, Gem 3, and at the end they arrive to the readout PCB, where they hit these strip readout bars, which then transmit the signal and amplify it, and transmit it to the electric components. In the GEMs, there are currently installed two types of GEMs in the CMS. The GE21, which stands for GEM NCAP second layer first ring, and the GE11, which stands for GEM NCAP first layer first ring. The oldest model is GE11, obviously, while the GE21 is more recent, and in fact is still being tested in the laboratory. Alongside the GEMs, there is CSCs, which are cathode strip chambers. In the near future, there will be installed even ME0, which are muon detector and cap 0, obviously. As I told in the last slide, in the future, we will have new kinds of GEMs. The GE21, which is already started to be used, which is composed by 4 modules, which constitute a single layer. And an early version has already been built in the laboratory, but the others are still being tested. We can say it like this. While the ME0 are made of 6 layers, which are assembled into a stack, and these chambers will be closer to the beam pipe, which means that they will have a higher rate, and so they will be more efficient. But this also means that we will require better electronics and materials, so they will be even more expensive. These kind of GEMs are still being tested. In fact, only prototypes have been built. Let's talk about our journey here at CERN. On our first day, we had the meeting with the supervisors, where they, how can I say, they gave us some general information about what GEMs are, how they work, and why they are so important. And in the afternoon of the day, we went to their lab, which is in Prevesan, where they showed us their laboratory and made us see how GEMS works.
On Wednesday, we visited the test beam in the north area, There was an experiment set up that you can see here. That one is a GEM prototype, 10 by 10, that has the same functions as the GEMs that are currently installed, but is smaller because it's a prototype. And there we did some testings, but not much because the beam was off the day. On Monday, we worked in the lab. There, we did some gem calibrations using an X-ray chamber and an oscillometer. Here you can see the signal that gems give off. This is the signal given off by cosmic radiations, while if we turn on the X-ray gun, we get this signal, which is, as you can see, much stronger, much higher sensitivity. We had to test how many events where we took the calculation. The X-ray gun that fired X-rays on our setup. On Mondays, we too got in the clean room where there were some gem layers that had to be cleaned for them to be assembled later. There you can see us cleaning the gem layers with an electrostatic roller, and then we had to effectuate some quality control to ensure that there was no residue left. And so there you can see us measuring the resistance of the gem layers with this machine. These ones were all past the quality control, so they will be installed in the CMS. On Tuesday, we did some more gem calibration. In particular, we had to check the energy of the intensity of the transmission. Here you can see some events that were caused by cadmium radioactive sample that we put on top of the gem. This cadmium radioactive object caused some energy peaks. In particular, its direct energy peak is the last one right here, while the Koppler fluorescence that is inside the gem caused the second peak, and the Koppler fluorescence buffed by the quenching gas caused this first peak. We had to do some data interpolation, as you can see here, using Root, which is a program offered by GEM, by the CERN, by CERN, to analyze data. And here, if you can see, there is a red line on top of our raw data. That is the interpolation of the of this graph. Here you can see the end result of the data we took, and this is the actual data that will be used to calibrate the gem that we were working on. On Wednesday, we went to the CMS control room, which is the brain of the CMS. There we saw some gems being operated. There you can see the display that shows the state of the gems. And that particular day, there were no problems. That's why you can see it. So it was all blue, which is a great sign. Then we stayed a bit in the CMS control room, where we also learned about CSCs from another group that was there, and where we were explaining some more things. On Thursday, we calibrated some VFATs that are these objects right here. VFATs are a part of the electronic components of the GEMS, and these are the ones that take in the data and then transmit it to the computers. This is the first layer of data analysis. Here, there are 128 channels that are connected to the 128 of the actual strips inside the CMS. So this object will be actually inside the CMS where it will take data. The calibration is necessary because when data is acquired, it doesn't go as planned. There is a lot of noise that are natural fluctuations of the electromagnetic field that cause graphs not to be straight lines, but for them to have points distributed along the area. So we had to adjust our our threshold. That's right. We had to adjust our threshold so as not to lose data if we had too high of a threshold. But at the same time, it had to be high enough not to show noise as actual data being taken and to contaminate the data. So we had to do some calculations with the data that were taken to find the sweet spot in which to put our threshold and then to calibrate perfectly each layer. There are various levels so that we can have the optimal functioning and data acquiring.
Special thanks to our supervisors, which are Giovanni and Brendan at the bottom of the room. And especially thank you to you all, to CERN, for the opportunity, and thanks.
Very good. Time for questions. I will start as usual. You and actually another group before mentioned the clean room, but maybe not everybody knows why clean rooms are so important and what do they are. Why do we call them clean room and what are they use them for and why people have to dress like that in a clean room?
So clean rooms, as the name says, are rooms, very clean rooms, that have no dust, and it has very low dust because it's impossible to have absolutely no dust. They are very, very important because these components are very thin and very delicate. As we have showed you in the first slides, there are no actual numbers here, but there are a few microns in height. And these holes are really microscopic. So it's important for them to not get plugged. So atoms can pass through them and multiply, so actually detect muons. Also, there is a very high difference in voltage between the layers. There is a high tension. So a single bit of dust would create a shortcut that would stop all the gem from working, and it would be a great loss of energy because, of course, a shortcut would allow a lot of current to flow and to heat up the gem, damaging it. That's why so we go in the clean rooms to build them and to test them, because of course they will work in a clean setting. They will only be surrounded by the working gases, so argon and CO2 and another small components. So to test that they actually work, we need to do it in a clean room where there is no dust and nothing that can interfere. We are clothed like this with caps and lab coats and gloves and masks to avoid bringing in any bit of dust that could contaminate the atmosphere. There is a quite a bit long procedure to get in. You need to walk on these sticky mats to avoid bringing in dust from your feet. You need to wear feet caps, and there are also some clothing requirements to getting in, as to avoid introducing any dust.
Thanks a lot. Other questions? No? Antonella?
Yeah, I have a question concerning the GEM technology, where you explained why CMS went for that technology. Did you discuss the, I don't know, other technologies and the reasons for using GEM instead of others?
So our team was only working on GEMs. Here in the lab, there are these are all GEM pieces. They have different shapes because they are assembled in modules, but it only works on GEMs. So everyone we talked to was working on GEMs. While on Thursday, when we went to the CMS, no, on Wednesday, when we went to the CMS control room, there we met some other people, obviously, because in the control room, everyone who works at CMS, everyone who has a project has a seat there. Here. In fact, this is not GEMs. These are not GEMs. And there we spent quite a lot of time talking to the people who operate the CSCs that are different muon detectors. Yes, there are different muon detectors. They are cathode strip chambers that to work with a gas, but they have a different structure. And GEMs are better.
Okay, thanks a lot again. Very nice presentation also from Giulia and Alessandro. And now, time to move